Hey, good morning, students. I hope you guys are all doing well, healthy and all that good stuff. Hey, today we're looking at light. We're going to specifically look at a couple different aspects of it. We're going to make sure we understand how it gets created or absorbed. We're going to then look at what it means to be quantized, which is an individual little chunks worth a certain amount of energy. We're going to describe the photoelectric effect, how it relates to semiconductors. And then we're also going to look at spectroscopy, which is the way of breaking up light into its different components and then identifying where that light came from, what attributes it has, stuff like that. It's going to be super important later for astronomy type stuff. So, before we get going, here's some vocab words we've been using so far. The blue ones are ones we're going to cover today. Green ones we should hopefully already know. If you guys want to talk about any of these, please stop by office hours. Those will be from 2 to 3 o'clock today, as well as on Wednesday and Friday this week. So 3 days a week for an hour. Hopefully that's working out for you guys. Can't make it, email me and I can always hop on some other time too. Okay, so getting started. There are two main sources of light. One of them is called blackbody radiation. The other one is from electrons moving around between orbitals around an atom. The first of those two categories, you're going to get kind of a continuous spread from like below red to above blue. So the full range of the spectrum. And we're going to look at some examples of that. And this, I attribute this mostly with thermal energy. So when something is warm, it's going to be emitting light. By the way, did I tell you guys that you all look radiant today? Now I actually can't see the colors you're glowing in, but you are glowing in infrared, microwave, and radio wave radiation because of your blackbody radiation. Um, let's see. But yeah, so it's there's going to be some distribution. It totally has to do with the thermal energy converting into light. It usually does this at spectrum below what we can see, so infrared and below. But if something gets super, super, super hot, then you can start to see it. So old school incandescent light bulb, the kind that got really hot, they were using black body radiation to make light. Okay, the other one is electrons being lifted or falling towards or away from the nucleus of an atom. So this has to do with the potential energy released by an electron as it falls. That's the second thing that could happen. This is going to give really distinct colors. It's not going to give all colors. And this is the one that helps us identify what kind of an atom is creating the light. So this is how we know about like faraway planets and stars and stuff what they're made out of. Whereas the black body radiation, that's going to tell us more what the temperature of the object is. So this one you can identify the temperature of something, and this kind you can identify the composition of something. And between these two kinds of light, you can tell a whole lot about distant, faraway objects as well as stuff in the lab too. So here's a chart for black body radiation. What's weird is if you look at the x-axis, it makes sense in terms of wavelength, but if you graphed it in terms of average temperature of the object, you would actually get the highest numbers on the left and the lowest numbers on the right. So what's really important is, you know how in art we always think, oh, blue is a cold color, red is a hot color? That is exactly 100% backwards of, the actual temperature versus color correspondence. So colder objects emit red, hotter objects emit blue. And then when you get a mix of multiple colors, then it might be white hot. So by the time you're getting substantial blue and green components, that's a white hot temperature color. What's pretty cool is you can, like I said, you can tell how hot something is. First of all, 3000 Kelvin, that's really hot. That's like a cool flame, maybe like flame of a candle or something. And what you might notice about this is that most of the light that it's emitting, first of all, there's not a lot of light. It's kind of dimmer in general than something that's hotter. But most of the light it's emitting is in the infrared range, below red. You can't see that, but you can kind of like feel it, put your hands up to it and feel warm. So if you're getting warmed up from a campfire, it's mostly infrared light that's being transferred to you. And that's from black body radiation in the fire. And so, yeah, you can't see most of that light, but it can warm you up. This is also how your toaster's cooking bread. Sure, it glows red a little bit, but most of the light that's being transferred to the toast is in the infrared range. But of the remaining colors that you can see, most of them are in the red yellow, which is why a typical candle might partly look orange. There's probably some sodium in the wick too. That's the other kind of light. We'll talk about that in a sec. But yeah. Whereas when something gets hotter, not only does it emit more light, on the y-axis, this is how much energy is being delivered. So we're not only getting more light, but it's also shifting towards the blue side of the spectrum. At the point when you got stuff that's crazy hot, like 7,000 Kelvin or like 10,000 Kelvin for like a star or something, then you're getting substantial amounts of light in the ultraviolet and even the X-ray and maybe even gamma spectrum, which again you can't see, but those are actually the ones we worry about for things like sunburn and stuff. So, we were on campus right now, I would be torching some brass to the point where you guys could see it start to glow cherry red, and then we'd know based on the colors about what the actual temperature is. I've used this idea once or twice before to figure out how hot a jet turbine was based on the color that it was glowing. You can tell something about its temperature by using a chart like this. And again, this is just like all kinds of different random colors of light coming out in a mix, and the mix is kind of defined by one of those curves. That's called a black body spectrum. Now there's a second thing you could do. This represents the nucleus of an atom right there. These rings represent potential places for a resonance of an electron's wave. In other words, where the electrons are resonating and hanging out. And what can happen is, if an electron falls, it gives its potential energy away. The energy turns into something, it'll turn into light instead. And it's saying that the amount of energy that we give away is proportional to the frequency. So more energy goes with the higher frequency, less energy goes with the lower frequency. H is a constant, it's just some number, it's called Planck's constant. You can look it up if you ever need it. I don't think we're going to do any math with this. But I need you guys to know that the bluer the light, the more energy. The redder the light, the less energy. It's directly proportional. So the farther something falls, the more potential energy it gives up, the higher the frequency of the light that's created. As that electron falls, a photon, an individual chunk of light shoots out. And we can actually, I worked in a lab once that worked with individual photons. I was doing some crazy stuff. But we had these like cables with like metal things stuck on them and lenses, and we were shooting individual photons through in a super, 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 super dark room, like as pitch black as you could possibly make it, detecting one photon at a time, working on photon entanglement, which is now what they use for quantum computing. It was like back in 1998 or something. Anyway, point is that you can have an individual piece of light. When you do, you call it a photon. That's referring to light as a particle, and it can be worth a chunk of energy that's worth an exact amount, according to this equation. So what's weird is that we think of light as kind of like a continuous stream, but it's actually individual pieces. And that's what we mean when we say quantized. And when you're working on a small enough scale to where you notice individual chunks instead of a continuous stream of energy, then you're working in what's called quantum physics. So if you ever hear the word quantum physics, which sounds super cool, all it means is you're working on a small enough scale where you notice the pieces individually and not as kind of a continuous flow of stuff. Anyway, point is, if you got all these different combinations of how far an electron can fall down, then you're going to get all these different combinations of what colors can come out as a result. And so this is called an emission spectrum, because light's being emitted, shot out by electrons falling, and different height combinations get you different colors. And those height combinations are defined by how many protons and well, not nobody cares about the neutrons, but how many protons you have in the nucleus. It's defined by which atom we're talking about. So different atoms will get different color combinations, and that means that each color combination is kind of like the fingerprint for an atom. Like here is, let's see, I think I've got a good picture coming up in a sec here. Nope, not that. Go to the next one. There we go. Okay, so here's hydrogen. Real simple color combo for a simple atom. Here's mercury. Here's neon. If you see one of these patterns coming out of an object, you know that that object is made out of that element. This is how we identify what things are made out of. It's called spectroscopy. Measuring the spectrum. Like a scope, like something that sees something, measures it, and then spectrum, spectroscopy. Say it twice real quick. Didn't stand to mispronounce this on the first couple tries. It's spectroscopy. Okay, so hydrogen. Again, real simple one here. By the way, keep in mind, is this all of the possible wavelengths? No, this is just the visible spectrum. 350 is kind of like as violet as you can see. About 750 is like the deepest, darkest red you can see. Beyond that is infrared. Beyond that is ultraviolet, my favorite color. So remember, this is just what you can see. There's a whole bunch that we can't see on either side of this chart as well. So again, you can tell what something's made out of just by the spectrum that it emits because of the way that electrons fall. And so with that, let's play around with a model of the atom. You guys are going to do some chemistry for just a sec. Here are different models of the atom. If you've had chemistry, you've heard of some of these. If you haven't, maybe it's coming up in your future sometime. Point is, this is a zoom in of us shooting white light at an atom. And this is assuming that the atom is a bouncy ball, which it most definitely is not. They also thought that it was like goo with an occasional electron in there. And this didn't quite work. And then they thought it was like a planet orbiting the star, but that wasn't right either. And then this is the first model that mostly works. This is probably the model too that we use in chemistry a lot because it's the simplest one that kind of sort of works. And it's the idea that an electron is a particle. So it's like a dot, like a ping pong ball. You can see that little blue electron going around there. See? And if you give it energy, you can jump it up higher. And then when it releases its energy, it falls back down. So this is kind of the most basic level we want to work with. And here's the problem. We know that electrons aren't just particles, they're also waves. This is called the wave-particle duality. It's both of those things at the same time. So you can think of it like a wave, and you can think of it like a particle, and there's truthfulness to both of those ideas. So here's a better model. Now you can see the electron as a resonant wave. You can see that it's a standing wave with some nodes and antinodes, which is what we talked about last time. So this is thinking about the electrons as a wave. And it actually explains why you can only get electrons around those dotted lines, those orbital pathways, and not in the black space in between them. So this really clearly matches and explains why electrons are only allowed in certain spots. And then if you think about it as a particle being lifted up or falling down, that also explains the energy coming from it absorbing or emitting light. You can look at different combinations. By the way, what we got going down here is a histogram of each time it emits or absorbs something, and it's breaking it down by color. It looks like this is wavelength, measured in nanometers, which is 10 to the minus 9 meters, very small wavelengths for light. And yeah, you can see that there's some different color combinations that are possible. Other combinations aren't possible. Is it possible to fall from in between the two dotted lines to in between the two dotted lines? No, because those aren't resonances where the wavelength matches up in a standing wave. Remember, a standing wave was an inbound wave and a reflected wave canceling out to make nodes where something didn't move and antinodes where it moves the most. We have to have a resonance, a standing wave system here. That was in our last topic. Very important. Last up, there's a whole bunch of uncertainty that's built into this. Not that we don't know, but that we aren't allowed to know. We'll probably not talk about too much in depth there. But here's a more sophisticated model. And this is, as far as we know, the most accurate model we've got of the electron cloud around an atom. It is still following all the correct principles of it being a wave and it being a particle, but it's got some added additional math mixed in there. And this is the one that matches with the experimental data. So basically, yeah, we can see how it behaves using spectroscopy, and we can make a mathematical model to predict what's happening inside the atom, back that up with some other evidence and thinking. And when those two things match up, we've got a good model. That's kind of how we understand what the atom is. So that was some important ideas from chemistry. If you had that before, hopefully that's a reminder. If you haven't, hopefully it's enough to get you started thinking. Oh, you can see some of the S, P, D, and F patterns we talked about last time. On last time's PowerPoint, we had that image of the drum head shaking in different arrangements. You can actually see the orbitals taking those same different arrangements over here. So as weird as this is like a drum head, except wrapped in a three-dimensional space around the nucleus of an atom. Hopefully that was some kind of crazy stuff for you. This is basically how atoms work with all the electrons around them. Okay, so coming back to some other stuff here. All right, so bottom line is that you can have individual photons carrying a certain amount of energy that's directly proportional to their frequency. Why would they do that? They could have gotten it from thermal energy, in which case you've got all kinds of different values possible, but they're distributed according to one of those graphs, and that's called blackbody radiation. Or you can have it coming from an electron falling towards a nucleus within fixed distances, which we saw in the models of the atom there. And when they do, they emit light that, again, is proportional to the frequency. Okay, that's pretty much it. Now, if we're in class right about now, we would get a good sodium plasma going.
You
This is one of
think
my
you've got a
favorites. It
Christmas
smells
pickle?
terrible. You
Check
guys
out
actually
the
might
one
be,
from the
be happy you're
Greensboro
home for this
Science
one. It
Center.
smells so bad. But you can basically put a couple thousand watts into a
Oh,
pickle
Wow.
just using 120
Yeah.
volt AC current, which, by the way, is super dangerous. You can electrocute yourself, so don't do this at home. And one thing you'll see is that the energy going in is causing the atoms to wiggle faster in the pickle. So did you notice that you've got steam shooting out both ends? That's because those atoms have been accelerated by the electricity. They've been given a lot of speed, which we would also call thermal energy at this point because it's small scale and disorganized. And that's why you got steam shooting out both ends. But the other thing that's happening is we're moving the electrons up away from the sodium atoms. Sodium is the salt in the pickle, it's part of the pickling brine. And by moving the electrons up, they're able to fall back down. When they do, they're emitting this characteristic orange glow that's associated with sodium vapor plasma. And you guys might actually have street lamps that glow that same orangey color. Some of the older ones do.
you've got a
They use
Christmas pickle?
mercury vapor now,
Check the Greensboro
but
Science
some of
Center.
the old street lamps would glow that exact same orange yellow color.
Oh,
And again,
yay!
that's a sodium
Yeah.
plasma in there. Pretty awesome. So yeah, someday maybe stop by next year. I'll run the pickle for you guys as a group if you can. It's a pretty fun one, even though it smells terrible. Okay, how do we know it's sodium, by the way? Oh, it's because sodium vapor always emits the same exact fingerprint-like characteristic called a emission spectrum for sodium. So there is that. All right, other stuff now. Now we're going to kind of switch topics. It might seem like it first. We're going to build a crystal out of silicon. Silicon is a semiconductor. If you've heard of semiconductors, metalloids, you've heard of the semiconductor industry, you've heard of Silicon Valley. All of our computer systems and electronics are using silicon crystals in different ways. So right here, we got a picture of a giant silicon crystal. Every once in a while, they sneak in an atom that's not silicon, but that's similar to it. What I want you to notice is silicon has 4 electrons in the outside layer. That's what those blue dots represent. Boron only has 3. Phosphorus only has 5. There are some other choices besides boron and phosphorus for ones with 3s and ones with 5. And if you had chemistry, you know about groups in the periodic table. Anyway, point is, this atom is a lot like silicon, trying hard to be very similar, especially when it's stuck in a crystal, trying to be friends with everybody. Those are covalent bonds. But what it's doing is it's missing an electron, and it sure would love to have that electron. Meanwhile, over here, this one's got 1 electron too many. This poor electron doesn't fit anywhere. It's like free. What occasionally happens is one of these extra electrons over here falls into place right here. This missing spot is called a hole. You can have this extra electron fall into a hole. Now, what did we just talk about with falling electrons? When an electron falls, it's giving up potential energy. And if it's giving up potential energy, the energy can come out as light. So by the way, if you have 2 different silicon crystal sections right next to each other, that's called a diode. Di for 2. This is a diode because it's got 2 different silicon crystal constructions next to it. So when an electron falls in a diode, one possibility is that it could be emitting light. So you might have a light emitting diode, an LED. You guys have all seen and heard of. So if an electron falls, it can give off light. That's one option. And the other thing you could do is you could reverse that process if you rebuilt this a different way. And you could have light come in, and let's say an electron had already fallen. There was already this one that had fallen over here. If you hit that with enough light, you could then use that energy to lift it back up. And you could lift it out of its hole, pop it to the other side of this junction, this connection piece, and then you could build up electrons over here, and they don't like building up. They repel each other. So once you get a pile of them, they're all trying to push each other apart, which means if they gave them a route to follow, they would go around a wire to get back to the other side. And at that point, you've got what's called a solar panel, photovoltaic cell. Now, here's a question that's kind of important. Do any frequencies or any wavelengths of light work to get this electron back over here, or vice versa? Do all frequencies work? And the answer is no. If you don't lift it up high enough, it just falls right back to where it was. So like, let's say there's a shelf right here, and I have a brick, and I lift the brick to here. Oh, you guys are probably stoked there's no brick today. Okay, so if I lift the brick to here and I let go, does it stay on the shelf? No, it never made it in the shelf. It falls right back down. If I lift it to here and I let go, does it work? No, it falls right back down. If I lift it to here and I let go, does it work? Yes, it makes it onto the shelf. So there's a minimum threshold, a minimum amount of energy you can put into this for it to work. And that means that things like radio waves, microwaves, infrared, they don't turn a solar panel on, no matter how much you put on there. You could put like a bazillion watts on a solar panel of infrared light, and it still wouldn't produce electricity. But if you even put just a little bit of visible light or ultraviolet light, you can actually get that solar panel going and making electricity right away. So you have to have the minimum frequency it takes for each individual photon to lift the electron the appropriate height. If it's not enough, the electron never makes it where it's going, and it just plops right back down and re-emits that light somehow else. Or it comes out as thermal energy or whatever. So what I have, if you're interested in more, is this was kind of one of the best examples of
Diodes have
explaining how
numerous
diodes
applications
work.
across the electronic industry, and they are an integral part of any electronic device. In this video, we will explore the inner workings and
You guys should
applications
check
of the
this out.
diode.
Yeah, so check that out. And then hit me up in office hours with questions, or if you want to talk about it some more. Some cool stuff here. Hopefully, you also get to the point in this video where it talks about transistors, which is how computers do their math and cell phones do their processing and all of our electronics work. Transistor is simply 3 areas instead of just 2. So 2 zones makes a diode. 3 zones makes a transistor. It's a little more complicated, but uses the same principles of how to use silicon crystals with an occasional impurity to move electrons around using electricity. So check that out. And that is it for today.